Welcome to the Greek ship Corrosion channel. My name is احتشام زاده. I'm a researcher in the field of corrosion and protection of materials. Chapter 2, Section 1, Thermodynamics of electrochemical reactions. The first law of thermodynamics. The main reference is Fundamentals of Electrochemical Corrosion, ASM International. How is the first law of thermodynamics stated? The first law of thermodynamics says that total energy of an isolated system is constant. Energy can neither be created nor be destroyed, but can be transformed from one form to another. Or the first law of thermodynamics states that the change in internal energy of a system is equal to the difference between the heat added to the system and the work done by the system. du equals Q minus W. Illustration of the first law of thermodynamics. D is used for a perfect differentiation of a function, and delta is used for demonstrating a large and finite change. State 1, State 2. Heat transfer, work done. Delta U equals Q minus W. The equation of the first law of thermodynamics. du, an incremental change in the internal energy. Q, heat absorbed by the system. W, work done by the system. If the process is conducted reversibly, the heat absorbed is T times ds. T, the absolute temperature. ds, the change in entropy associated with the process. It's useful to consider the work term as divided between P times dV work and other work. P times dV work associated with volume changes of the system doing work on or receiving work from the surrounding atmosphere, and other work considered here as electrical, which will be designated as W prime. W equals P times the volume change plus W prime R. R stands for reversible case. P times the volume change is the work term associated with volume changes of the system. W prime R any other work, here as electrical work. The reversible case is then written as du equals T times ds minus P times dV minus W prime R, which on rearrangement becomes du minus T times ds plus P times dV equals negative W prime R. The left hand side of this expression is the differential of the function u minus T times S plus P times V taken at constant T and P. Thus, the differential of the function u minus T times S plus P times V is the differential of the internal energy minus T, the differential of the entropy, plus P times the differential of the volume, or the differential of the function u minus T times S plus P times V is equal to negative W prime R. Enthalpy and Gibbs free energy relationship. The expression u plus P times V naturally arises in thermodynamics and is called the enthalpy, H. Thus, H equals U plus P times V. The entire expression U minus T times S plus P times V, remember that U is the internal energy, T is the temperature, S is the entropy, P is the pressure, and V is the volume, which was shown to naturally develop by this argument, is called the Gibbs free energy, G. Thus, G is equal to U plus P times V minus T times S is equal to H minus T times S. Thus, the differential of the Gibbs free energy is equal to the negative W prime R, or the negative differential of Gibbs free energy is equal to W prime R, reversible, constant T and P. For convenience, the Gibbs free energy or Gibbs function is indicated by GFE, reversible and irreversible change. The negative differential of Gibbs free energy is equal to W prime R is true for a reversible process, essentially at equilibrium, carried out at constant T and P. So the maximum work over and above that associated with the volume change is given by the decrease in the Gibbs free energy. In the reversible process, the heat effect Q is equal to T times the entropy change, and work against the environment P times the volume change are inherently associated with the process. However, the heat effect Q will be equal to T times the entropy change only if the process is reversible. P times the volume change will be the work effect against the environment only if the process is reversibly carried out. Although from a practical standpoint, reversibility is not as critical for this term as for the heat term. When a process is considered whether it represents a small, incremental, or large change, definite, definable initial and final states exist. For each of these states, the thermodynamics variables have definite values characteristics of the state. Thus, Gibbs free energy, entropy, volume, etc. each undergoes specific changes for the system regardless of whether the change is brought about reversibly. The product T times the entropy change, however, which in principle can be calculated, will equal the experimentally observed heat effect only if the process occurs irreversibly. Since for a given increment of a process, du is the same whether it is brought about reversibly and irreversibly. Since internal energy of a system is a state function, it does not depend on how the system got from the initial to the final state. An increment change in the internal energy is equal to Qi minus Wi is equal to Qr minus Wr, where the subscripts indicate irreversible and reversible cases. Consider an irreversible process in which no W prime work is actually done. Again, it can be done if the process is conducted reversibly. Then, an increment change in the internal energy is equal to Qi minus P times the volume change is equal to Qr minus P times the volume change minus W prime R, or Qi minus Qr is equal to the negative W prime R. When work W prime R is done by the system, W prime R will be positive and thus Qr is greater than Qi. It should be remembered that Q is taken as positive for heat absorbed by the system and negative for heat rejected to the environment. Therefore, for systems undergoing reactions that liberate heat, negative Q values, for example chemical or electrochemical reactions, the absolute value of the irreversible heat is greater than the absolute value of the reversible heat. The absolute value of heat rejected irreversibly to the environment is greater than the absolute value of the heat rejected reversibly to the environment. The significant conclusion. The conclusion is that more heat is rejected by the system and hence absorbed by the surroundings in the irreversible case. Specifically, the magnitude of the extra heat is that of the work W prime R, which could have been realized in the reversible process. Hence, since the negative Gibbs free energy change is equal to W prime R at constant T and P, the negative Gibbs free energy change is the energy available from the process and represents either useful work if the process is permitted to occur reversibly or extra heat rejected to the environment, which importantly can never be used isothermally to do the work otherwise possible. Since this energy, the Gibbs free energy change, is not a part of the energy change associated with T times the entropy change or P times the volume change, both of which are fixed inherently by the process, it can be said that this energy is spontaneously available and that from a thermodynamics viewpoint, the process can occur spontaneously. Thus, the condition for a spontaneous process is that the negative Gibbs free energy change is greater than 0 or the Gibbs free energy change is less than 0 at constant temperature and pressure. Thank you for your time. Challenge number 11. If you like to challenge yourself, please answer this question in the comments below. What does this figure illustrate? The horizontal axis is the volume, the vertical axis is the pressure. The reference of this challenge is Thermodynamics and Kinetics in Materials Science, Oxford University Press.